Hello, this will be our lecture number 4 in strength of materials. In this lecture, we will deal with bending loads. So in lecture number 2, we talked about axial loading when we had a force normal to the cross section, so along the axis. So this was about axial loading. In the previous lecture, we talked about torsion when we had a torque trying to twist the shaft. And today we'll talk about bending. In the previous lectures, we talked about the stress and strain and how the axial loading and or the torsional loading can create stresses and strains inside the bar or inside the shaft. But today we'll not talk about that directly. We have something else that we need to learn before going to the stress and strain analysis. So before we start, just some reminder about stuff that we already know. So in the first lecture, we defined what we call supports. So we said they have what we defined were three types of supports. So the roller or the pin and the embedment. So the roller constraint or the roller supports, it restricts the motion only in one direction. So it will not go down. So the vertical direction is restricted by the horizontal one is not restricted, so it can move in the horizontal direction. That's why we'll have only a reaction force in the vertical direction, preventing the system here from moving vertically. While on the other hand, in a pin constraint and a pin support, the system cannot move neither horizontally, neither vertically, nor vertically, but it can rotate. So the idea here is that because it cannot move, so if we try to move it horizontally, it will create a resistance force, horizontal resistance force, reaction force. If we try to move it vertically, it will create a vertical reaction force. So here we have two reaction forces, two components. And finally, the embedment, we said if I have this symbol here, so the embedment prevents all type of motion, cannot move horizontally, cannot move vertically, and at the same time also cannot rotate. If we try to rotate it, we'll create a reaction moment here. So these are the three supports that we defined, and we will be using them during the lecture. Also another refreshment, stuff that we did for the axial loading and for the torsional loading, but I will repeat it here only for the axial force. So we defined what we call axial force diagram. For example, let's take this example here. We have an embedded bar here, embedded in a wall. We have some loads applied, external loads. We have something trying to pull it here by a force P, while here we are trying to push it into the middle with a force P over 2. So we said to draw the axial force diagram, we said because here we have external axial forces, we have at every point inside the bar, we will have internal axial forces. And the idea is to draw the variation of this internal axial force in each portion of the bar. So the first step to do, we said, is to draw the free body diagram. So here, because we have only horizontal forces, so we are trying to pull or push the bar, so we'll have only a reaction force. We don't have any moment here. We don't have any force trying to rotate the bar. We don't have any lateral force. We don't have any vertical force. So the only reaction force will be horizontal. If we do sum of r's equal to 0, we can find that r is equal to p over 2 to the left. After that, we said we can make a cut here. So we can make any cut between this point and this point. We can make it in the middle here. Any point that will give me the same result, because always I don't have any force acting here or here. So if I make a random cut in the middle here, so if I have a force here, I should have an internal axial force. So we take it always going to the right. So this is what we call the internal normal force. We call it an internal axial force. And because of the equilibrium in this portion here, because sum of force is equal to 0, we can see here that n is equal to r equal to p over 2. So every time I make a section anywhere here between this point and this point, I will have always n is equal to p over 2. So in this portion, always the internal axial force, the internal normal force, is p over 2. However, if I do a cut here and isolate this portion, so if I make a cut here and isolate this portion here, I will have different results. So I will not do the cut here. So I make a cut here and isolate, I find. If I make a cut here, I should take p over 2 also into account. So I isolate all this portion, and I will find n equal to p. So that's what we did in the second lecture. So we can see that the internal normal force in this portion is different than this portion. Every time I have axial external axial load, I need to make a new cut to check what will happen here. So that's the idea. Now what we will do in this lecture, we do the same but for bending loads, and we will see it's more complicated. It's way more complicated than the axial force diagram. So the whole lecture will be about how to draw the diagram when we have lateral forces instead of axial forces. So let's start by defining first what do we mean by bending. So before we start with bending, we talk about pure bending. So when we say a beam is in pure bending, is under pure bending, it means that we have an external moment applied at the two ends of the beam. So if I have an external moment here and an external moment here, these two moments we call them bending moments. So this is different than torsion. Torsion, the moment was around the axis of the shaft. Here is not around the axis. Here the moment we'll try to do here, it will try to bend the beam in this direction like this. The torsion tried to twist. Here we try to bend it like this. So there's the difference. Here we call it moment. We don't use the word torque. We call it bending moment. So the external moment here is constant. So when we say m is different than m of x, which means that the moment does not vary with x. So that's why it's a constant moment. If I have a constant moment here and a constant moment here, equal but opposite in direction, so we can say we have what we call pure bending. So r here is what we call the radius of the curvature. So because the beam will become a curve due to the bending on the right and on the left. So this is what we call pure bending. So for example here, what will happen here if we make a cut here and I isolate this portion? Now the beam is in equilibrium, and any portion of the beam also is in equilibrium. So if I make a cut here, now I don't have any force here, so sum of force is equal to 0, but I have also sum of moments equal to 0, which means that I should have an internal moment here that should balance the external moment here. So the internal bending moment, it will exist to have sum of moments equal to 0. So we can see that at every point, everywhere I make a cut and isolate the portion, I will have this is what we call internal bending moment equal to the external moment. That's only valid in the case of pure bending. So pure bending when I have two moments on the right and on the left trying to bend the beam. So this will be a very simple case. Now what we will study here is when we have a non-uniform bending. So non-uniform bending occurs when the moment is not constant. I don't have only two moments on the right and on the left. So let's take direct example here. So what do we have here? We have a beam supported by a pin support here and by a roller support here, and we have a mass here, a weight. So what type of forces we will have here? We have the weight will be acting downwards. We have a reaction force here and reaction force here. So here, as you can see, the force of the weight is not normal, it's not axial loading. This will be what we call a lateral force. When we say a lateral force, when we say lateral force, it means a force perpendicular to the axis of the beam. It's perpendicular to the beam. It's not normal. It's not perpendicular to the surface. It's perpendicular to the beam itself. So here in this case, we will see later that lateral forces, even if I don't have a moment directly, lateral forces will cause bending. So this one will not be a pure bending because it's not due to an external moment on the right and on the left. And the internal forces in the beam that we will see, like in the case of axial loads, we found that the internal force will be also internal axial loads, the N, that we called N. Here we see that the lateral force, when the forces are perpendicular to the beam itself, they will create inside shear forces. And also they may create what also internal bending moment, like the one that we saw before. So let's take this example here. So the same example here. So if we draw the free body diagram, we have the weight of the box that we had on the beam. We have a reaction at B and a reaction at A. So what we'll expect here, because the box, the weight here is applying a force, we can expect that the beam will go down. And here, because we have the support, the beam cannot move vertically, so it will stay at the same position. Here also the beam will not move, so we can expect that the beam will have a curve-like shape like this due to the bending, due to the lateral force. Now the equation of this curve, we will try to define it in the next lectures. So not in this lecture. So in the next lecture, we will see how will the beam bend? How will be the equation of this line after bending? But what we care about here in this lecture is that if I have lateral forces, they will cause also bending. But this will be a non-uniform bending, not pure bending. And as we said, they create shear forces and internal bending moment. So let's take another example here, and to check how do we find these shear forces and internal shear forces and internal bending moment. So let's take this example. We have a beam embedded here in a wall. The beam embedded in the wall, let's say I have a distributed load here Q, or distributed over a length equal to L over 4, with L being the total length of the beam. So we have an embedded beam on the left L over 4 of the beam. We have a distributed load Q. So in this example, we revise also what's meant by a distributed load. So we said the distributed load Q is in Newton per meter. It's equivalent to a force equal to Q times L over 4, as if I have a force equal to QL over 4 applied in the middle here. So it's the same as having a distributed load. So we can use the integral form to find the force applied by Q and the moment, or we can say that we can replace this by a force equal to Q times L over 4 and applied in the middle of L over 4. The first step, if we want to study this system, is to draw the free body diagram. Now, because we have here, embedment here, so the embedment will prevent motion in vertical direction. It will prevent motion. It will also prevent rotating. So it will create inside here a reaction moment and a reaction force. So the reaction moment, we can take it in any direction we want. It can be positive or negative, depending on the direction that we choose. And also a reaction forces. So normally we have Rx and Ry, but we know here that the Rx will be equal to 0 because there are no forces trying to pull or push the beam. So I don't have any reaction. The wall will not react. The wall will prevent motion in vertical direction. So Ry will be equal to the force applied by Q, and Mr will be equal to the moment applied by Q. So let's find the Rx, Ry, and Mr. So here, so in this example here, we don't need to find, let's not calculate now the Rx, Ry, and Mr. So this example here, let's just see what will happen inside. So normally the first step will be always to find the reaction forces. The Ry will be equal to QL over 4, and the Mr will be equal to the moment applied by Q around this point. So let's see what will happen inside the beam in this case. So let's see, like we did for the case of axial load, let's make a cut here and see what will happen inside. So if I isolate this portion here, now the system is in equilibrium here. So the system is in equilibrium here. If I make a cut here, all the system is in equilibrium, and also this portion should be in equilibrium. In this case here, what should we have here in order to equilibrate the system to have a balance? We should have a shear force, an internal force, and internal moment. So how will be the direction of the internal force in this case? It should be vertical, because I have vertical forces, because the horizontal force is 0, reaction force. So I should have a vertical force in order to balance the Ry, and I should have also a moment in order to balance the presence of Mr. So let's see. So this is what we call, like in the case of axial loading, we had a force N. Here we call it V and M. And also in the axial load, we had the N always going out to the outside. Here, if I isolate like this, we take, by convention, we take the force, the internal force that's created here, we call it V. And we take it going downwards, and the moment M, which is created also in order to balance Mr, is we take it going counterclockwise. So by convention, every time we make a cut and we make the cut on the left, for example, I isolate the left portion, we take V going downwards and M. So what are V and M? V is the internal force which is created in order to balance the lateral forces here, and M is the internal moment created in order to balance the external moment here. V and M, both of them are a result of the equilibrium of the portion here. So V, as you can see, is what? Is not normal to the cross section here, is tangent to the cross section. What do we call a force which is tangent to the cross section? We call it a shear force. So that's why the lateral force will create shear forces. Like in the case of axial loading, we have internal normal forces. Here we have internal shear forces. And at the same time, in addition to the internal shear force, we'll also have an internal bending moment. So at any point in the beam, if I make any cut at any point, always I will have a shear force going downwards by convention, we said, and internal moment counterclockwise by convention, which will balance the presence of the moment here. If I isolate this portion here, I will have the same. I will also have a shear force which is equal to this one, and an internal bending moment. But by convention also, if I isolate the right portion, I take V going up and the M going clockwise. So at any cut here or here or here, always I will have an internal shear force and internal bending moment in order to have an equilibrium of the portions that you are isolating. What our objective here in this lecture is to draw the variation of V and M at any point, like we did for the diagram of axial forces of normal force. Now we want to draw a diagram of V and M to see how V and M vary at any point in a beam when the beam is subject to lateral forces, so subject to bending. So that's the objective of this lecture. So we said, so to repeat, V and M represent respectively the internal shear force and the internal bending moment, which are created at any point in order to have equilibrium. And our objective is to draw the variation of V and M along the beam. So we need to understand that V and M at any point depend on the external load, what we call Q of X, applied on the beam. So here's a very important point. We need to differentiate between Q of X that we just defined now and the Q here. So Q of X is a general parameter. So it's a parameter that we can use for any beam. So let's take this example here, and the example that we just studied. For example, between the point 0 and the point 3L over 4, before we have the Q here. What's the external load? Do we have any external load here? No, we don't have any external load here. The beam is not subject to any lateral force. So we can see that between 0 and L3L over 4, the external lateral load is 0. So Q of X is equal to 0 here. Here, between 3L over 4 and L, do we have any load? Yes, we have external load Q in Newton per meter. It's a constant. So Q of X here will be equal to Q. So Q of X is equal to 0 when we don't have any external load. It will be equal to a constant when we have a distributed load, like is the case here. So between 3L over 4 and L, Q of X will be equal to Q. So Q of X is a general parameter that can be defined to any beam. We just need to see in a given interval if we have an external distributed load or not. If we have external concentrated force, we don't take it into account here. We'll see that later how we deal with the concentrated force, not the distributed loads like this. So that's the definition of Q of X. So it's a general case for any beam. Now let's take a general beam and any beam that we know. Let's take a portion of the beam and isolate this portion. Let's take a portion, a very small portion of size dx, the length is dx, and let's isolate this portion here. So the applied load Q of X, as we said, the Q of X can be 0 if I don't have any load, can be constant if I have a distributed load, but in the general case, let's keep it Q of X, which depends on the case that we have. So the applied load Q of X, we have, if we look at the left, like we said, by convention, the right side here, if I isolate this portion, so V plus dV, let's say that V is varying at every point, so here will be V plus dV and M plus dM, while here I will have V and M. So these are the loads applied on this isolated portion. So the isolated portion, I have Q of X, I will have V and M on its left, and I have V plus dV and M plus dM on its right after I moved at the distance of dx. Now the objective what's the objective of this slide here is just to show how V will vary as function of Qx. So what's the relation? How will V vary after a distance dx as a function of Qx, and the same for the internal bending moment. So to repeat, V and M are the internal shear force and the internal bending moment which are created at any point in the beam due to the presence of lateral forces due to bending. So now let's study this isolated portion here. So this isolated portion, because this isolated portion is also in equilibrium, sum of forces equal to 0. What are the sum of forces equal to 0? So we don't care about the moment for now. Sum of forces equal to 0. We have V going up, so plus V minus V plus dV. And what's the force applied by Q? So Q of x, as we said, can be replaced as if I have a force F, and let's call it FQ, is equal to Qx times dx, always the distributed load times the distance. And this force will be applied in the middle of the x. So minus Qx dx. So the three forces acting, we have V minus V plus dV minus Qx dx. If we rearrange these terms here, we can find, finally, that's what we know from all the slide, that Q of x is equal to minus dV over dx. What does this mean? That the variation of the shear, the internal shear force that we are trying to find as function of, with respect to x, the derivative of the shear force with respect to x is equal to minus Q of x. Why is this helpful? So this means that if I have the external load applied at any point, I can find the shear force, because this is our objective. Our objective is to find the shear force at any point. So between 2 points, I can find the variation of the shear force. We will see later how we will use this in order to find the shear force at any point. But what we need to memorize from this is dV over dx is equal to minus Q of x. So then its variation, the derivative of the internal shear force as function with respect to x is equal to minus the external load applied in the interval. The same for the moment. If we do the sum of moments equal to 0 here, for example, around this red dot here, we'll have m. Let's take clockwise, the clockwise direction as a positive direction. So we have plus m minus m plus dm in the opposite direction. The moment applied by v around this point will be the force times the distance, so plus v times dx, because plus v times dx is in the clockwise direction. And finally, the last force applying a moment around this dot here is Q of x. So Q of x dx, that's the force times the distance, will equal to dx over 2. So minus because it's counterclockwise, so minus Qx dx times dx over 2. Now if we rearrange also these terms, and with this term here can be neglected compared to these terms here, because as you can see here we have dx squared, so it's a second order term, and when we talk about very small dx, the dx squared can be neglected as far, with respect to the other terms. So by neglecting this term here and taking into account these terms here, we can find that dm over dx is equal to v. What does this mean? That the variation, the derivative of the internal moment with respect to x is equal to the internal shear force. So in the previous slide we said that if I have the external load I can find the shear force. Now we are saying that if I have the shear force I can find the moment by just integrating the shear force. So dm over dx is equal to v. So now we can say that d2m over dx2, so the second derivative of the internal moment with respect to x is equal to dv over dx is equal to the derivative of v. So if I derivate this one time over the x, and dv over the x, and from the previous slide is equal to minus q of x. From all the three slides that we just learned, this is what we need to use. dm over dx is equal to v, and dv over dx is equal to minus q of x. Why do we need to use this? What's our objective? To repeat, our objective is to find v at any point, the internal shear force created at any point. So if I have the external load at any point, I can find the internal force at any point. And after that, once I find v using q of x, now I can, so q of x is always given. So q of x is given, I can find v. After I find v, I can find the internal bending moment. But now what I'm saying here is very simple, but when we see later that if I want to apply this in complicated problems, it will be a bit difficult. So let's see. So before using these relations here, let's take this simply supported beam. The question is, draw the shear and moment diagram. So when you say shear and moment diagrams, means that try to find the shear force, the internal shear force and the internal moment that will be created at any point, and draw the diagram. Draw this variation of the shear force and moment at any point, like we did for the diagram of axial force when we drew the variation of the force n at any point. Now we need to draw the variation of v and n at any point. So let's start. So before using the integration relations that we just derived, because this problem is, as you can see, is simple. We just have a simply supported beam. We have a pin support here and a roller support here and a force in the middle. Let's try to do it like we did, like we used to do in the axial force. So how do we do it? So the first step is always to find the reaction forces. Now the reaction force is here. As you can see, the force is applied in the middle. Because on the pin support I have normally I have a horizontal and vertical reaction forces, while on the roller support I will have only a vertical reaction. But here just we can see very quickly that r1x is equal to 0. I don't have any horizontal force other than it. So sum of forces in x is equal to 0. It will give me r1x equal to 0. The second point, I can see that f is equal to r1y plus r2y. I don't need to do a lot of calculation because of the symmetry of the problem, because f is applied in the middle. We can see directly that r1y will be equal to r2y will be equal to f over 2. Now we can do the calculations. We can say sum of moments around a point equal to 0. Because here, but here we don't need to do that. We can see it directly from the symmetry. If I neglect this r1 of because r1x equal to 0, so r1y and r2y, both of them will have f over 2. So now we found the f over 2. We have the free body diagram. We have f over 2 here, f here, and f over 2 here. Now if I want to find v of x and m of x at every point in the beam, that's the objective always. Now if I don't want to use the derivative equations that we found in the previous slide, if I want to do it the way that we used to do with the axial force, so how do we do? For example, here I need to make a cut at any point here between this point here in the middle here, and isolate a portion. So I make a cut here. I can make it here or here. It will be the same. From a distance x, let's say the distance x. The distance is varying here. So from a distance x, let's call this point here A. So if I make a cut, like we said, if I have lateral forces here, as you can see, I have lateral forces. I don't have axial forces. Lateral forces are perpendicular to the beam itself here, trying to bend it. So the beam will bend like this because I have the force F here, so I have bending here. So we said if I have lateral forces, every time I make a cut, instead of having a normal force N, we will have a shear force V of X and a bending moment M. So I have V and M. Now we call it V of X and M of X here because we call this distance here X. So what do we have in this isolated portion here? What do we have? We have F over 2. So if I take sum of force equal to 0, it will give me that in this point V is equal to F over 2. Sum of moments around A equal to 0. F over 2, the moment of F over 2 is 0 because it passes through the point. So what are the moments around the point A? I will have V of X, V times the distance, V times X, clockwise, minus M of X equal to 0. It will give me M of X equal to F over 2 times x. So at any point x here I do a cut, I will have always v of x equal to f over 2 and m of x equal to f over 2 times x. So you can try to do any cut here and isolate the left portion, always will have this result between 0 and L over 2. Now let's do this. Now here between L over 2 and L it will be a different story. Why? Because now we have another force that we should take into account when we isolate the left portion, which is F. So let's make any cut here also between L over 2 and L. And also the same concept here, I isolate the first portion here, the portion I can also isolate the right portion, but because we are following the same convention everywhere, let's always isolate the left part, take V going down and M counterclockwise. So also the distance x now will be from A to the point. Also, if I do sum of force equal to 0 here, I will have V of x that I'm trying to calculate minus F plus F over 2 equal to 0 will give me V of x equal to minus F over 2. Here, so here v of x plus f minus f over 2 is equal to 0. And v of x will be equal to minus f over 2 here. If I also do the sum of moments around A equal to 0, it will give me, so f over 2 will not have any moment, f times L over 2 plus v of x times x minus m of x equal to 0. And then it will give me m of x is equal to fl over 2 minus f over 2x. So this is a way to find the v of x and m of x. So we take a cut like we did for the axial force diagram. We make a cut here, we isolate, we see the v and m, which values I will have. we make another cut here and we see the same v and m, which value they will get. As you can see here, now I can find that the moment at any point x, so v of x between 0 and L over 2 is constant here. It will be always equal to f over 2, while between L over 2 and L it will be equal to minus f over 2. For the moment here it will be f over 2 times x, which means that the moment will vary with x. Here it will be 0, here it will be f over 2 times L over 2, because here x is equal to L over 2. So for the m of x here, it will be fl over 2 minus f over 2x, but here x is between L over 2 and L, because now we are isolating this portion here. So the first equations here are valid from 0 to L over 2, while the second equations here are valid from L over 2 to L. So now if I want to draw a diagram, v of x is equal constant here and equal to minus f over 2 here. That's what we found. If I want to draw them as instead of using equation, I want to draw diagrams. The second relation here, between 0 and L over 2m is equal to f over 2x. So it will start from 0 until fl over 4. And between L over 2 and L, it will be fl over 2 minus f over 2x. So it will go from this point here. For L over 2, it will be fl over 4 going to 0. So this is the method if I want to use the method that we did this for the axial force. If I want to make a cut every time, and in every cut I need to find V going down and M. And as you can see, even for a very simple problem like this, it can be a bit complicated. Now for more complicated problems, it will be a lot more difficult in order, especially when we have external moments, especially when we have distributed loads and so on. So what we do now, we try to use the derivative equations in order to learn what we call a graphical method. So instead of trying to find the equation, we try directly to draw the diagrams directly from the beam itself, and after that we can find the equations from the diagram. It will be the opposite way. So let's take the same example here. But before doing that, let's say how do we use the derivative, because the derivative equations will be very useful for the graphs. So what we said at the beginning, q of x is equal to minus dv over dx. So the derivative of v with respect to x will give me the external load. So if I have the external load, by doing integration, I can find v. So the slope of the shear force is the applied load Q. So the slope of the shear force will be the applied load, but we don't forget the negative sign. We'll see that later. And here's the same. When we set the internal moment, after I found V using Q, I can find now M. Now the slope of the bending moment will be the shear force. So let's see what will this mean. The shear force curve will be continuous. So if I have the external load, unless there's an external point force on the beam, the curve goes up when the force is upwards. The same, the bending moment curve is continuous unless there's an external point moment. We will see all of this in examples now. The shear force will be 0 at each end of the beam unless a force is applied at the end, and the bending moment will be 0 at each end of the beam unless a moment is applied at the end. The curves goes up when the moment is clockwise. So all of these relations here that are found using the derivation relations here, we will see them how we apply them directly in the graphs in the examples. That's very important here. The change in shear force between any two locations is equal to the area under the distributed load curve, and the change in bending moment between any two locations is equal to the area under the shear diagram. So these two slides here, this slide number 20 and 21, they have 1, 2, 3, 4, and 5, 6 sentences here. These six relations here will allow us to draw directly the shear force diagram and the bending moment diagram. So these 6 relations here that we have in these two slides, if we apply them, we will be able to draw. It will be a bit complicated, but with this practice it will be way easier than trying to make a cut everywhere every time. So let's take the first example that we just did and see how we can apply these 6 relations here in order to draw the shear force diagram. So directly here, let's say this is the example that we just had. I have F over 2 here, F over 2 here, and a force F in the middle here. So without making a cut here and making a cut here, this is the relation that we know. We know that dv of d over dx is equal to minus q of x. So we said the q of x is the external load. So between 0 and L over 2, what's the external load here? 0. I don't have any external load. Between L over 2 and L, what is the external load here is also 0. So this is a very simple problem that you are trying to solve now. Now let's see how we draw the shear. So the first step, let's directly start with the diagram. Let's put the diagram and see how we can draw the shear force diagram. So the shear force curve, I'm writing here one of the 6 relations that we found. So the shear force curve is continuous unless there's an external point force acting on the beam. The curve goes up when the force is upwards. So here, let's start from this point here. What do we have at this point here? We have a force F over 2. So the curve goes up when I have an external point force on the beam. Here we have an external point. Point force means a force applied at a point, not a distributed load. So F over 2 here. So the curve will go here by F over 2 directly. So we know that the curve will start by F over 2. After that, the shear force curve is continuous unless there is an external point force acting on the beam. So here is very important. We know that dV over dx is equal to minus q of x. If q of x is 0, like it's the case here, what does mean q of x is 0? Which means that the derivative of v with respect to x is 0. What do you mean dv over dx is 0? Which means v is a constant. So when the derivative is 0, which means that the function is constant. So dv over dx is 0 here, which means that the shear force is constant. Which means that on this, between 0 and L over 2, the shear force is constant. It will always equal F over 2, because dv over dx is 0. Here, what do we have here? So the shear force curve is continuous unless there's an external point force acting on the beam. What do we have here on the L over 2? We have an external point force going down. So the curve goes up when the force is upwards. Here the force is downwards, so the curve should goes down. So here it was F over 2. It will go down by how much? By F, by the amount of F. So F over 2, here it will go down by F. So F over 2 minus F, it will go to minus F over 2. Because I have F over 2, we go down by F, it will be minus F over 2. The same here, between L over 2 and L here, from this point to this point, we don't have any external load. The Q is 0, so dV over dx is 0. So the shear force is constant. And then here we go back to, from minus F over 2, we go with F over 2 here. So this is the shear force diagram. Now we start by F over 2. After that, we don't have any external load, so the shear force is constant. Here I have an external point force going down by F, so I go down by F very simply here. Then here I don't have an external load, it's constant. So instead of making a cut here and a cut here and trying to find directly, we can find them graphically here. Now let's check the same, but for the moment diagram. So the moment diagram, now we need to draw. Now after we found the shear force diagram, the objective is to find the internal bending moment diagram, knowing that dm over dx is equal to v of x. So here, after I found the shear force diagram, now I need to find the bending moment diagram, knowing that the derivative of m over dx with respect to x is the shear force. Here I don't forget, I need to put always in mind the free body diagram of the beam that I have. This is the beam that we have here. Now also we put the diagram before we start drawing. Here we need to use two concepts. The first one, these two concepts come from this relation here, that the bending moment will be 0 at each end of the beam unless a moment is applied at the end. The curve goes up when we have a moment when the moment is clockwise. So here the bending moment will be 0 at each end of the beam unless a moment is applied at the end. Here in our beam, do we have any moment applied at the end? Here, let's start with this end here. Do we have any moment applied? No, we have only reaction force. So the moment will start from 0. That's it, because we don't have any moment here acting. Now, here, dm over dx is equal to v of x. So here, what do we know about v here? V is what? Is constant. So the derivative of m with respect to x is a constant. What is, if the v is a line here, is a constant, what will be m? It will be a linear variation. Why? Because we know that the derivative of a line will be a constant value. So if I have a constant value, the integration will be a line. So that's a concept that we need also to keep in mind. If v was equal to 0, this one will be a constant. If this one is a constant, this one will be a line. If this one is a line, this one will be a parabola, and so on. Now, why this line is going upwards? Because the constant is positive, and we know that dm over dx is a positive constant, so this one be a line going upwards. So this is the main concept that we will be using. Graphically, we need to know that the integration of a constant will be a linear variation. But what we don't know here, so we know it's a line now, we don't know what will be the value here. Here, instead of doing also calculations and doing integrations and calculations, we can directly use the second concept. The change in bending moment between any two locations is equal to the area under the shear diagram. Where's the shear diagram? This is the shear diagram. Between any two locations is equal to the area under the shear diagram. What are the locations that we are trying to find here? We know here that the moment is 0. We need to find the moment here after L over 2. So this is the two locations that we are talking about, between 0 and L over 2. What's written here that the change in bending moment, the change between this point and this point, so is equal to what? To the area under the shear diagram. So between 0 and L over 2, what is the shear diagram? This is the shear diagram. Between 0 and L over 2, it's between this point and this point. What is the area under the shear diagram between 0 and L over 2? It's the area of this rectangle here. What is the area of this rectangle here? It's f over 2, this constant here, f over 2 times L over 2. So f over 2 times L over 2 is equal to fL over 4. So we know that the change between this point and this point is equal to fL over 4, because it's the area under the shear diagram. And we know here it's already 0, so 0 plus fL over 4 will give us to fL over 4. So let's repeat quickly. We know that m is equal to 0 here because we don't have any moment. Because the shear force is a constant, a positive constant, so the integration of the positive constant will be a line going upwards. To find the point here, so we draw a line, but we don't know the exact value here. To find the exact value here, we need to find the area under the shear diagram between this point and this point. What is the area under the shear diagram? It's this is the area of this rectangle. What's the area of this rectangle? Is f over 2, which is the value here, times the area of a rectangle is the base or the height times the base, which is f over 2 times L over 2, because the distance from here to here is L over 2, and the value here is f over 2. So f over 2 times L over 2 is fL over 4. So the variation between this point and this point will be fL over 4, and this point was already equal to 0, so this one will be fL over 4. That's what we did here. Now let's try to apply the same concept here. Now here we need to understand that also if I don't have any external point moment here, the bending moment curve will be continuous. What does it mean that will be continuous? That here I will keep going from this point. I can go up or can go constant. I need to continue on this point. I can't have a line like this one here. I can't have a line going downwards here or go. Why? Because I don't have any external moment acting here. I just have an external force. The external force here, the F, does not change the continuity of the bending moment. So what I need to know that I don't go, for example, here went from F over 2 to minus F over 2. Here I have FL over 4. I need to stay at the FL over 4. Now in next example, we can see an example where we need to when we might have a jump here, but here we need to continue from FL over 4. Now we need to check here. Now our relation is based on our diagram is based on this relation here. So here the same concept here. What happened to V here? Now V is always also a constant. What does it mean if V is a constant? V is a constant means that V is a constant means that the bending moment is a line. What type of constant is V? V is a negative constant. If V is a negative constant, means that the line should be going downwards. Now we don't know where it will stop here, but we know that before now I put it here 0 because of the symmetry. But let's assume that I don't know where it will stop here, and let's say I want to check this point here where it will be. So we know that it's a line. If I want to, so the change of the moment between this point here, between FL over 4 and this point that I want to find is equal to the area under the shear diagram. What is the area of this? So what's the area of under the shear diagram between L over 2 and L? It's the area under this rectangle here. What is the area under this rectangle here? It's minus F over 2 times L over 2. So it will be minus FL over 4. So the relation will be minus FL over 4. So that's the rectangle here, minus FL over 4. And I already have I have FL over 4. So FL over 4 minus FL over 4, it will take me to 0. So we drew the moment diagram between 0 and L. So every time we need to know the point of start. After that, we need to check the shape of variation of the moment. If it's a line, if it's a parabola, if it's a constant, if this line is it going upwards, if it is it going downwards, depending on the sign of the shear. And after that, in order to find the value between two locations, I just find the area under the shear diagram between the two locations. So the same problem that we did before. Here we did the opposite. Directly we found this diagram and we found this diagram. And after that, we can derive the equations from the diagram. We can see that here is constant f over 2, here is constant minus f over 2. Here is linear going from 0 to fl over 4. So we can directly find f over 2 of times x. So at L over 2 is equal to FL over 4. Between L over 2 and L, also it's a linear, but starting from FL over 4 minus F over 2. So we can see that the slope of the m, if I make the derivative of m, it will give me v. Here the same thing, the derivative of m, it will give me v. Here, how do we find the equation? So how to find the equation? This is a mathematical relation. I have a line, I need to find the equation of this line. So this will be a mathematical practice. We can do it later, and you can see it in the other example, and we can do it during the practice sessions. But you should be familiar with how to find an equation of a curve. But we need to understand that the slope of the m is v, and this between 0 and L over 2, and between L over 2 and L. So this problem that we did here, it's considered a simple problem here because we just have a force in the middle. But let's take another example which can be a bit more complicated. So let's take this example here. Always we have the relation is always valid. The derivative of m is v, and the derivative of v is minus q. This is always valid. Let's take this example here. We have an embedded beam. We have between 0 and L over 4 we don't have any load. Between 3 L over 4 and L we don't have any load. But between L over 4 and 3L over 4, we have a constant distributed load Q. And now our objective is to find the shear force diagram and the bending moment diagram using the graphical method. Now, if you want to use the initial method, we need to make a cut here, we need to make a cut here, and we need to make a cut here. And the cut here, it will be a bit complicated because we'll have a Q of x, so it will be a marker. That's why the graphical method can be more useful, even if it looks more complicated at the beginning. But once we get used to it, it will be easier to use. Now, as usual, the first step always is to draw the free body diagram and to find the reaction forces. Here we can see that Rx is equal to 0 because we don't have any, we just have lateral forces. Ry is equal to Q times L over 2. And Mr, what is the value of Mr here? So to find Mr, we draw sum of moments equal to 0 around this point, let's say. What are the moments around this point? We'll have plus Mr. And what is the moment applied by Q around this point here? So to find the moment, the easiest way is to say that Q is equivalent to a force equal to QL over 2 applied in the middle of L over 2. So it will be QL over 2 applied in the middle here. The distance between this force QL over 2 and A will be equal to L over 4 plus L over 4. So we can do this practice also to find Mr, but you need to find Mr is equal to minus QL square over 4. So now we have Ry going upwards, QL over 2. We have Mr clockwise. If I take it in the clockwise direction, is equal to minus QL square over 4. Using these forces, now we need to find the shear force diagram and the internal moment diagram. So as we did in the previous problem, we have a QL over 2 here, we have a Q. So for the shear force diagram, we don't care about the moment, we just care about the forces. So the shear force diagram here, we put V and X. So let's do like we did in the previous problem. So here at the beginning, what do we have? We have at the 0 here, we have a QL over 2 going up. So we start by QL over 2 on the top. Between 0 and L over 4, we don't have any load, so Q is 0, which means V is constant, like we did in the previous problem. So V is constant here, don't have any load. Here, here's very important. Now, this is a new point here that we didn't see in the previous example. Here, between L over 4 and 3L over 4, Q is what? Is a constant. So Q is a constant. What does it mean Q is a constant? When Q is constant, which means V is what? Is a line. So V should be a line. Now the line is going upwards or going downwards. Q is what? Is a positive here. Q is positive, and we have already a minus. So if Q is positive, the shear for Q is a positive constant, means that the V is a line going downwards because we have a minus sign here. So that's the difference between V and M. So if Q is positive and a constant, so V is a line going downwards. So the line is going downwards. Also, let's assume I don't have where it will arrive here. So here's the Q is equal at this point QL over 2. We need to find the point here. It's the same like we did before. The change in shear force between any two locations is equal to the area under the distributed loaded curve. Distributed load curve. What is the change between this point here and this point here? Is the area under the distributed load curve. What's the area under this curve here? It's the Q times L over 2. So Q times L over 2. The load is Q times L over 2. So QL over 2. So we know that I have QL over 2, and I will go down by QL over 2. So the point here will be 0. After that, I don't have any external load here, so the shear force will be constant, equal to 0. So the Q is 0, so I will keep constant here. So let's repeat. We start by QL over 2, by a force going up. Here I don't have any load, so the Q is 0, so V is constant. Here I have a constant distributed load Q going, a constant distributed load Q, a positive Q. So, and I have a minus sign here, so because it's constant, this one should be aligned. Because I have the minus sign here, it will be going down. How I can find this value here? I know that the value here was QL over 2. Now I need to find the change between this point and this point. We know that the change between this point and this point is equal to the area under the distributed load. What's the area under the distributed load here? Is the area of this rectangle here. What's the area of this rectangle? Is Q times the distance. So Q is the load times L over 2. So QL over 2, that's the area of, I have already a QL over 2. I will go down by QL over 2, so I will reach 0 here. After that, here I don't have any distributed load. I will continue as a constant, so which is equal to 0. So now we found directly the shear force diagram here. Now that I found the shear force diagram, now our objective is to find what? The bending moment diagram. To find the bending moment diagram here, as you can see, I draw this line here just to show that I will have a variation here. So L over 4, L over 2, and L over 4 here. So now let's check how we start with the bending moment. So the bending moment, we said that if I don't have any moment around this point here, I will start with 0. But here, as you can see, we have a moment due to the embedment, minus QL square over 4. So the curves goes up when the moment is counted as clockwise. So that means that if the moment here is clockwise, I direct to put the value as it is. For example, if the moment here is minus QL square over 4 clockwise, I will start by minus QL square over 4. Let's say when you found the reaction force, you chose to take the moment in the counterclockwise direction. So you will have a QL square over 4 counterclockwise. If I had a moment QL square over 4 counterclockwise, I can say, so it means so I need always to convert it into clockwise value. That's what's important. So always find the value in the clockwise direction here and then put it here. So every time I have a clockwise, I put the value as it is. If it was in counterclockwise, I take the opposite sign and I put it. So that's the objective here. So we know that we need to start by minus QL square over 4. Now we need to check what type of variation it will have. It will have a constant, it will be linear, it will be parabolic. Let's see how we do this. To do that, we look at V. What do we know about V here? V is what? Is a positive constant. So it's a constant, means that m is linear. Positive means that m will go upwards. So that we know that it's a positive constant. So this will be a linear because V is constant, and going upwards because V is a positive constant. I don't have a minus here like in the case of Q. So here minus QL squared over 4 going upwards. Now we need to find the value here. How do we find the value here? We know that the change of the moment between this point and this point is equal to the area under the shear force between this point and this point, between 0 and L over 4. What is the area under the shear force here? It's the area of this rectangle here. What is the area of this rectangle? Is QL over 2 times L over 4. So area of this rectangle is QL over 2 times L over 4 is QL squared over 8. So the change will be equal to QL squared over 8. So I had already minus QL squared over 4. I need to go up by QL squared over 8. So if I take minus QL squared over 4 plus QL squared over 8, it will give me minus QL squared over 8. So that's it. So let's repeat quickly. I know it's linear going upwards. The change between this point and this point is equal to the area under the shear force diagram is equal to EQL squared over 8. So the change between this point and this point is equal to plus QL squared over 8. So I just add the QL squared over 8 to this value, and I will find here minus QL squared over 8. Now here at this point here, do I have here at this point any external moment? No, so no, I know that I should continue from this point. I don't have a jump here. I keep on the same point. Now let's check here. What type of variation does V have here? If V was constant, I know that M is linear. But now V itself is linear. So what do we know about M? If V is linear, which means that M here, I draw it, it looks like a line, but here this is a parabolic variation. So we know that if V is a line, now M is a parabola here. So M is a parabolic variation. Now I draw it here going to 0, but normally I should not know where it should be going. So I know this will be parabola. The second step is I need to check what will be the value of M at this point here. So let's make it here clearer. So let's say I don't know where to go. I know that it should be a parabola. I put in my mind that it should be a parabolic variation like this. I don't know this point, what will be the value at this point here. So to find the value at this point, we use always the same concept. The variation between this point here, between the moment at this point and the moment at this point, is equal to the area under the shear curve. What is the type of area I have here? Because it's a line, I will have this triangle here. So the area of this triangle will give me the change of moment between this point and this point. So what is the area of this triangle here? I have QL over 2 times L over QL over 2 here times L over 2 times 1 over 2 because it's a triangle. So the area is 1 over 2 base times height. So 1 over 2 times QL over 2 times L over 2. It will give me what? 1 over 2 QL over 2 times QL over 2. It will give me QL squared over 8. So the variation between this point and this point is equal to the area of this triangle here. And also the parabola is going upwards because the shear force here is positive, even if it's going down, but it's a positive value here. So here we know that it will go up by QL squared over 8. What does this mean? So minus QL, I had already minus QL squared over 8. The variation between this point and this point is QL squared over 8. So I should go from here to 0. So this point should be 0 because we found that. So the first step always, I know that is parabola. I find the value of the second point here using the area here. And then I can see where this point will be. So that's why I don't normally draw the diagram until I find the point here. For example, here we found that the point here should be equal to 0 because minus QL squared over 8 plus QL squared over 8. So now we need to modify the diagram in order to put this value here. Because we know now it's reached 0 here. So this is the value here. And after that, what will happen here? What is the value of V here between 3L over 4 and L? V here is 0. So V is 0, which means what? That M is constant. And M was already equal to 0, so M will also be equal to 0. So this is an example also when we have different type of variations. Every time I know the shape of variation. Is it a line? Is it constant? Is it a parabola? After that, if I know it's a parabola or a line, I know I can find what will be the second point using that the variation between any 2 points is equal to the area under the shear force diagram. And after that, I can draw my diagram, which will be, I can find here, this is if I want to draw the diagrams. Now I can find the relation. I can see that between 0 and L over 4, this one is a constant, equal QL over 2. Between L over 4 and 3L over 4, I can see it's a line, so QL over 2 minus Q. So you can see that the slope is equal to Q here. X minus L, we are starting by L over 4, so now you need to draw the equation of this line. And finally, between 3L over 4 and L, we can see that the Vx is equal to 0. Now for the moment, we can see that between 0 and L over 4, the moment is started by minus QL square over 4 plus QL over 2 times X. Now how do I find the slope here? It's very simple. I just look at here because know that the V is the derivative of M. So the slope of this of X here should be QL over 2. After that, between L over 4 and 3L over 4, we can see that M of X is equal to 3QL over 4X. So just the equation of this parabola here. So if I can integrate here, I will have 3QL over X minus QX squared over 2. And to find this constant, I just take any point here or any point here. I know that the moment here is equal to minus QL squared over 8, and I can find this constant. So to find the equations, it will be a different story. So the objective here is to draw the diagram and to find the moment at given points. Later, to find the moment, we just use the integration, and we can use also the curve in order to find at given points. So the objective here is just in this lecture is to learn how to draw the diagram, and after that, if asked, we need to find the shear force and the bending moment equation. Now for this lecture, we don't need to find the equations. It will not be the priority. The priority is to find the shear and bending moment diagram. But in next lectures, to find the equation of the moment, especially in the last lecture, it will be important in order to be able to solve the problem. So let's take now a third example. Now this example here that I made, this example here, it summarizes, I guess it contains all, is a very complicated one, where we can see in this example all the possible combinations that we might have in a shear and moment diagram problem. So let's say I made this simply supported beam. Let's say I have a concentrated force here. I have a distributed force between 0 and L. I have a concentrated force. So the total length here is 4L. Between L and 2L, I have a distributed load Q. At 3L here, around this point here, I have an external moment M1. And here I have a roller support. So we have an external concentrated force, a point force P1. We have a distributed load Q, and we have also a constant or a point moment M1. All of these three are external forces, in addition to the reaction here and the reaction here. So this simply supported beam is subjected to several external loads. Distributed load Q, concentrated load P1 is equal to 4QL. So P1 is given here as equal, as a given information is that P1 is equal to 4 times Q times L. So this distributed load Q, we know that it will create a force QL applied in the middle of L here. So P1 is equal to 4QL. We have a distributed load Q is equal to Q, and moment M1 is equal to 16QL squared. So these are the values are given. The question is to draw the shear and bending moment diagrams. So as always, the first step is to find the reactions at A. So at A, I'll have RAX and RAY. At B, I will have RBY. So P1 is given equal to 4QL and M1 is equal to 16QL squared. So RAX is equal to 0 here because we don't have any force in the horizontal direction other than RAX. A sum of Fi equal to 0, I will have RAY plus RBY minus P1 minus QL equal to 0. And P1 is equal to 4QL, so we can find RAY plus RBY is equal to 5QL. And sum of moments around A is equal to 0. So P1L plus QL times the distance is equal to L plus L over 2, because we said the Q is a force, as if I have a force QL applied at L over 2 here. So distance from QL to A is equal to L plus L over 2. What else we have? We have RBY times 4L, and also we have the moment, because the external moment is applied everywhere. Even this is very important. Like when we say sum of force equal to 0, we apply the force everywhere. So even I am taking the moment around A. If I have a moment here or a moment here, I need to include it in the sum of moments around A. Now, as if the problem wasn't complicated enough, look at these values: 61 over 8 QL minus 21 over 8 QL. Okay, so let's continue with these values, even if they are a little bit complicated. So let's see how we will. Now, after we found the final reaction force is a crucial point. It's a very important point. We found RAY, RBY. So we have a 61 QL over 8 here. We have minus 21 QL over 8 here. We have P1 is equal to 4 QL and M1 is equal to 16 QL square. Everything is given now. Let's start. We put our beam here. We put all the forces acting. Let's put the shear force and let's start drawing the shear force. Where do we start with the shear force? We'll start at 61 QL over 8 here. Okay. So 61 QL over 8, we start with this point. Do we have any external load here? No, 0. The external load is 0, which means that the shear force is a constant. What do we have here? So 61 QL over 8. What do we have here? We have a force P1 going downwards. What does this mean? That I need to go here down by how much? By the value of P1, by 4 QL. So it will give me 29 QL over 8. So 61 QL over 8 minus 4 QL, it will give me 29 QL over 8. So now I need to go, I have a small jump here, that's what we said. So normally the shear is continuous unless I have an external point force. If this force was going up, I need to go up by 4 QL. So here I went down by minus 29 QL over 8. Now here, between L and 2L here, what do we have? We have a distributed load Q, a constant. So Q is constant, means that V is what? A linear. We know that dV over dx is equal to minus Q here. So the linear line should be going down. So we know that it should be a line going down. We draw a line going down. Now if I want to find the value here, what will be the value here? The value here, I need to find, it will be equal to the area under the load. Under the load. What is the area under the load between L and 2L here? Is the area of this rectangle. What is the area of this rectangle? Is Q times L. So Q times L. So I need to go down here by how much? By Q times L. So 29 QL over 8 minus QL it will give me 21 QL over 8. So I will come here to 21 QL over 8. So to repeat very quickly, I know here is a constant. So the V should be a line. To find the value at this point here, I just need to find the area under the rectangle, which is equal to QL. So I need to go down by QL. So the problem here is that we have 29 over 8, so that's a bit complicated to deal with, but it's not a problem. We keep the fraction. Then here between 2L and 3L, do we have we don't have any external load. Between 3L and 4L we don't have any external load. So here, because I don't have the Q is 0 here, so V is a constant, so I continue as a constant here. So you see we found the shear force diagram. So it's even it was a bit complicated, but we found it finally. So just to okay, so everything is fine now. So to repeat very quickly, so 61 QL over 8, we start. We don't have any load. The shear force is constant. We go down by V1. We go down as a line, and the difference between the point here and the point here is equal to the area of the rectangle here. After that, so we found 21 kl over 8. After that, we don't have any load until the end. As you can see, the moment here has no effect on the shear force diagram because we just care about the forces. Now let's do the same now for the for now. Let's find the bending moment diagram. Now after we found the shear force, so we need to keep this always in mind. So let's say where we will start here. Do we have any moment applied around A here? No. Directly around A? No. So here we start from 0. After that, between 0, so between 0 and here, I don't have any external moment. Until getting to the point here, I will not have any external moment, point moment. So I don't have any point moment around A. Now between 0 and L, what type of V, what do we know about V? V is what is a constant. So V is equal to 61 QL over 8. V is a constant means that M should be a line. And we know that dm over dx is equal to v. V is a positive constant, so m should be a line going upwards. What is the value of the? How do I find the value of the point of the m at this point here? The difference between m here and here, the variation of m between this point and this point is equal to the area of this rectangle here. So what is the area of this rectangle here? Is 61 QL over 8 times L. So we know that the variation between this point and this point will be equal to 61 QL square over 8. When we're already starting from 0, so we go to 61 QL square over 8. Now between this point and this point, what type of variation do we have for V? V is a line. What does it mean V is a line? So M is a parabola because M is the integration of V. And do we have any external point moment here acting? No, we just have forces, so we continue from the same point. We don't have any jump here. So a parabola going up because V is a positive value here. V is a positive value minus Q. We found it from Q. So here 61 QL square over 8. We need to find the point here. In fact, now to find the point here, what will be the point? We know that the variation of the moment between this point and this point is equal to the area of this trapeze between L and 2L. So the area of I have 29 QL over 8 here, I have 21 QL over 8 here, and I have a length L. How do we find the area? The area of the trapeze is equal to 20, so the larger base plus the smaller base, so 29.8 QL plus 21 over 8 QL times the height. It will give us how much? 25 QL square over 8. So the area of the trapeze is 1 over 2, the larger base plus the smaller base times the height over 2. So we find that the 25 QL square over 8. So the area of this trapeze is 25 QL square over 8. So we know that we need to go from 61 QL square over 8. We go up by 25 QL square over 8. So if we add this value to the variation between the 2 points, it will give me 43 QL square over 4. After that, what do we have here? So at 2L, between 2L, do we have any moment here? No, so the curve will continue from this point. So between 3L and L, what do we know about V is a constant? What does mean V is a constant? V is a constant means that that M is a line, and because V is positive, it means that M is a line going up. How much it will go up from 43 QL square over 4? It will go up by the area of this rectangle. What is the area of this rectangle here? Is 21 QL over 8 times L. So 21 QL square over L. So I need to add 21 QL square over L over 8 to this value in order to give me the moment at this point. So I have this value here, 107 QL square over 8. After I found this value here, I need to continue. So do we have an external moment acting around this point? Yes, we have an external moment around this point. What is the value of this moment? Is 16 QL square. Is this moment clockwise or counterclockwise? It's counterclockwise. So what does this how will this moment affect my diagram here? Like in the case of force one, we have a force P1 here, it will create a jump here. Also the moment here, the external moment here, it will create a jump. This jump is down or up. If the moment is counterclockwise, we will go down. If the moment is clockwise, we go up. So the moment here is counterclockwise. So we'll go down by how much? We'll go from my 107 QL squared over 8 minus 16 LQL squared, the value of M1. So we need to, yes, to reduce 16 QL over, to subtract 16 QL squared over 8 from the 107. So 107 QL squared over 8 minus 16 QL squared, it will give me minus 21 over 8 QL squared over 8. So I have this jump here. I need to pay attention. Normally, if I don't have any moment, it will continue the curve. But because I have this moment here, I need to stop and go down by the value of the moment, if the moment is counterclockwise. After that, from 3L to 4L, I have what? I have the V is a constant, so M is a line going up, and it will go up by how much? By the area of this rectangle. What is the area of this rectangle? It's 21 QL squared over 8. So I go up, it's a line, and going up by 21 QL squared over 8, it will go to 0, because I will add 21 QL squared over 8 to minus 20 L squared over 8 is equal to 0. Now once I reach the 0 here, I know that my diagram is correct. I can verify. Why? Because I should have 0 here, because I don't have also any external moment around point moment around B. If I know I don't have any point moment around B, which means that that I have the the bending moment will be 0, like at the point here is 0. So as you can see, this problem is very complicated, but we need to understand the difference between any 2 points is equal to the area. So the difference between this point and this point is the area of this rectangle. Between this point and this point is the area of this trapeze. Between this point and this point is the area of this rectangle. If I have an external, I don't have any external moment on these points here, so I always continue from the same point. Here I have an external moment around this point, so I need to go up or down. If the moment is counterclockwise, I'll go down by the value of the moment. So now we found the shear force and the bending moment diagram. So this will be the end of the lecture. We will have the time during the practice and to solve many problems about the shear and moment diagrams. So it can seem complicated, but with practice it should become easier.